Hi, everybody. Welcome to this session with the Yingjun. We can have it all with streaming databases and stream processing and real-time OLAP. This is Yingjun, CEO of Rising Wave. Thank you.
All right, thanks. Thanks for having me here. And today, I'll be talking about bridging stream processing and real-time OLAP. Can we have it all? My name is Yingjun Wu, and I'm the founder of Rising Wave Labs. Prior to starting this company, and we are 3.5-year-old company. And prior to starting this company, I was at AWS Redshift, which is a data warehouse, right? And before that, I was doing research at IBM Research Armadan. So my research area and my focus, industry focus is all about stream processing, RTB database, OLAP databases. And right now, what I'm doing, as I just mentioned, I'm a CEO and founder of Rising Wave Labs. And what we're doing is essentially an open source SQL streaming database that can allow people to do stream processing easily in a database way. The other way to think about it is that people can just use their database system to do stream processing. So we want to achieve two goals. One is that we want to make sure that stream processing is extremely easy to use, right? Well, because nowadays, if you talk to people about stream processing, they will feel scary, right? Well, they will feel that, stream processing is so difficult to do, so difficult to program, so difficult to develop, and I don't really want to have stream processing. So one of our goals is to make sure that stream processing is extremely easy to use. And second goal is that we want to make sure that stream processing is extremely cost efficient to run, because different from the other systems. Think about the Snowflake. You probably can turn on the virtual warehouse and turn off when you use it, and turn it off when you do not really use it, right, during the weekend, right? But for stream processing, typically it's 724. You have to run it all the time. So we always need to guarantee that it's super cost efficient. So about the stream processing, not just limited to Rising Wave, but about the stream processing, what we can do is about the streaming analytics, right? Dashboarding, and probably we can do real-time monitoring, alerting, real-time ETL, and probably database replication, database synchronization, all these kind of things, right? So yeah, that's about the stream processing and Rising Wave. So now let's talk about some applications, right? Well, this is RTA Summit, Real-Time Analytics Summit, and we all talk about the real-time. So what real-time means? Well, real-time definitely means that for low latency, right? We definitely want to see the result, the dashboard within the refresh result every single probably seconds, right? But typically, for real-time, no matter whether it's stream processing or real-time OLAP, most of use cases are edge recommendation, network monitoring, stock dashboarding, travel booking, and probably IoT computing, right? Fraud detection, all these kind of use cases, right? There are some other use cases like high frequency trading. People probably ask, okay, whether I can do high frequency trading, using stream processing technology. Definitely you can do that, but if you talk to those who are quant trading guys, we will tell you that they actually have specialized systems specifically designed for their trading platform. So they do not really use those general purpose because it's hard-coded with their trading algorithm. So they do not really use such kind of general purpose stream processing or real-time OLAP database systems. And if you want to do machine learning training or probably data science, I also don't really think that stream processing and real-time OLAP is a good system for you, right? If you want to do machine learning training, probably you can use some other systems like TensorFlow, like PyTorch, like some others, right? And so specifically stream processing and real-time OLAP focus on real-time applications, as I just listed here. So typically what people do is that, where the data comes from. We talk about the application, then where the data comes from. Typically in a big company, actually not a big company, but typically in a company, real-time or data-driven company, they have the data from the operational databases like Postgres, MySQL, Kafka, or some others, right? And they also have the messaging queues like Kafka, like Pausa, Kinesis, right, and many others, right? They actually have the data ingested from these database systems or these systems. And then now they want to gain real-time insights, right? So I really want to know, okay, what happened over the last 1 minute. I probably really want to know, okay, how my data changed, how my data get changed over the last probably 30 seconds, right? That's what people need, and that's what real-time is. That's what they really need to have a system for gaining real-time insights. But what kind of system we do to extract real-time insights? Well, there are two types of systems. One is the stream processing system, and the other one is real-time OLAP. For stream processing, I mean, people definitely use Rising Wave, and people talk about Flink, and if you come from the Kafka world, then probably you are more familiar with KSQLDB. But for real time, definitely there are Pinot, right? And Druid also hasn't been there for years, and there are some other embedded database systems like DuckDB. DuckDB can also do some real-time OLAP if the data set is pretty small, right? Can fit into your laptop, right? Definitely, it's also an option. But in general, we are not trying to compare about, okay, how DuckDB compares to Pinot, or how Rising Wave compares to Flink. We don't really focus on that part in this talk. We focus on how stream processing is different from real-time OLAP, or whether we can use these two types of systems together, or we just need to have one single type of systems, right? That's our talk is about. And today, to answer this question, we actually need to go through the history, right? How these two different technologies will get evolved, right? And the similarities and the differences, and then let's talk about the use cases. So first, let's talk about the history. How do the stream processing and OLAP database systems evolve? If we take a look at the history, we will find that for stream processing, both stream processing and OLAP systems have already been evolved for probably 20 or 30 years, right? And if you ever started working probably 20 years ago, you probably know that there are some systems called Natera, right? And also Green Plum. But for stream processing, it's actually it actually first came from academia. There were some research prototypes called Stream, called Niagara CQ, called Aurora. It's not that AWS Aurora, it's a research prototype, and Boreas. And these systems were developed first in universities like MIT and Stanford. And then, and that's when, and these kind of technologies were born around 2002 for stream processing. So let's look at how the OLAP database systems evolved. Okay, now, as I just mentioned, 20 years ago, we probably have Natera and Green Plum. And then we enter the big data age, right? And we have the Hadoop, Spark, then Redshift. Redshift is also for OLAP, right? But it's definitely not for real-time OLAP. And then gradually, we have the Druid, Pinot, and then these days we got DuckDB. But for stream processing, how this kind of technology evolved? Well, I mean, it's evolved from the research prototype, and then we have the Storm, Samza, S4, Flink, all these kind of big data systems. Nowadays, we have the KSQLDB and Rising Wave and some other systems. So from this history, we can find that initially, all these databases, both of these technologies started in the database domain, right? For research prototypes, we actually have the system called the streaming database, and also nowadays we also call it the streaming database. Basically, the researchers think about, okay, how we can allow database system to do real-time monitoring applications. The first paper about the stream processing was actually how to enable a database system for monitoring application. And in the OLAP world, similarly, the OLAP technology comes from the database world. You know that's what Natera and the Green Plum, Vertica are all database systems, right? But because of the MapReduce, the paper was published in 2004. Because of MapReduce, people think that, okay, probably we don't need to have a database. We probably can just have a stream processing engine or the OLAP engine, right? And that's why we have the people started building all kinds of data processing engines like Spark, like Flink, like Hadoop, like Hive is built on top of Hadoop, right? And some others, right? But more recently, we come back to the database. We actually bring back these technologies to the database systems. That's why we have the modern database systems like RaisingWave, like Pinot, right? These are all database systems. But RaisingWave is a database for stream processing, while Pinot is a database for the real-time OLAP, right? So why we have such kind of why people evolved from database to the stream processing to the database data processing engine, and then evolve back to database systems. So definitely, as I just mentioned in this figure, MapReduce play an important role, right? MapReduce, the idea of MapReduce was that, okay, we can essentially scale the computation across different in-community machines, right? I probably have 10 machines, 20 machines in my cluster, and we can just run the system, run the computation in those commodity machines inside of paying IBM, paying Oracle a huge amount of money, right? Because these guys, well, I mean, Oracle, IBM, DB2 are super expensive. But we don't really want to purchase those kind of systems, and then we just want to run the systems cheaply. We want to run the computation cheaply, right? That's why MapReduce was invented. So MapReduce exposed the lower level APIs you have to program in Java, right? Well, if you come from the Hadoop world, you know that's how it looks like, right? You have to programming, okay, map function and the reduce function. Those are the lower level APIs. They didn't really have a SQL interface 20 years ago, right? And also for MapReduce, it doesn't really have the storage, right? You cannot store data in Hadoop. You actually need to maintain your HDFS, right? That's Hadoop, right? Similarly, in Spark, Spark can also doesn't really store data, right? Well, even in these days, well, I mean, Spark doesn't really store data. They actually encourage you to store data in the Delta Lake, right? So essentially, MapReduce definitely has a greater advantage, and it allows you to do the computation in computed machines. But the problem is that it actually sacrifices the simplicity, right? Because it exposes a lower level APIs compared to the database, it's definitely more complicated, and you actually need to hire a lot of engineers to write the Java code, right? That's how it works. And also, the second thing it sacrificed is about the performance, right? MapReduce is definitely high performance, but essentially compared to database systems, it's not that performant. Why? It's not because I'm saying that, okay, Hadoop is not, well, I mean, these guys do not know how to program. Definitely not. Well, these are experts. These are excellent people, right? The reason here is that, I mean, for database systems, database essentially understands so database essentially understands your data storage, right? And because I understand the data format, I can build and I understand the statistics, right? Like histogram, I have a better understanding of the data, so I can build a better query plan to run a query on top of my data. That's why database is actually better for performance, right? So that's about the MapReduce, and to summarize, well, it definitely solved the problem of scaling computations in computed machines, but it sacrifices simplicity and also sacrifices performance. Now let's talk about the modern real-time OLAP and the stream processing systems. So what's the similarities between these two types of technologies? Well, for modern OLAP databases and stream processing, well, they both focus on simplicity. Nobody really want to, I mean, definitely people would love to write Java code, but not everyone understands how to write Java, right? So if you talk to business guys, well, they have no idea about how to write in Java, and they are probably more willing to write in SQL, right? So definitely for modern real-time OLAP and the stream processing systems, we provide SQL. And also, we actually manage the data storage. Nowadays, if you tell people that, okay, look, well, you actually have to match your own HDFS, the people will think that, well, you're crazy. You're kind of crazy because, well, I mean, they do not really know how to match HDFS. They actually love to use a system like Snowflake that can match everything for them. Right? For modern real-time OLAP and stream processing systems, same story. We actually manage the database. We actually manage the data for our users. Users do not need to create a HDFS, manage their own HDFS. Right? That's kind of crazy. Or their distributed storage system. That's kind of complicated. And the second thing for modern real-time, the second similarity between the real-time OLAP and the stream processing is about performance. They do care a lot about the performance. And how we care a lot about performance. Definitely, we dedicated a lot of engineering resources into building a better better system, right? Definitely, that's one reason. But again, it's more we can nowadays because we have the SQL, we actually can build a SQL optimizer to optimize the query. And second thing, as I just mentioned, in a database system, we know the layout of the data. So we have a better understanding of the data format and the data statistics. So actually, I can build a better query plan for the query plan for the user, so that we can always run the query efficiently, right? Otherwise, if we do not have such kind of information, you have no idea about how to tune your query, right? So that's the second reason. That's the second similarity is. Another similarity between the real-time OLAP databases and the stream processing system is the architecture, internal architecture. When we started, when we built the, big data systems, well, people think about, okay, look, well, whether I can scale my system in my own clusters. Well, my cluster have 10 machines, 10 or 20 machines. How I can scale it in these 10 machines or these 20 machines? But for modern real-time OLAP and stream processing systems, we think about how we can scale the system in the cloud. In the cloud, there's unlimited number of machines. Well, definitely I don't know how many machines AWS have, but well, you can imagine that you will never consume all the machines from AWS, right? So the goal is quite different. For MapReduce style systems like Spark and Flink, they actually think about, okay, how I can manage, how I can scale across within a certain fixed amount of machines, right? So essentially, to achieve the best performance, they use a technology called decoupled and compute and storage architecture, which means that, well, the data is actually located in the computation node, so that the single computation node, within a single computation node, it only need to access the data or do computation on top of its own data, right? Well, the data co-located with that machine. So that's the compute and the coupled compute and storage architecture. But what about the modern real-time OLAP and the stream processing systems? Think about the writing wave and think about the Pinot. We all go to a direction that we actually need to leverage technology called the decoupled compute and storage architecture. Why? Because again, we do not really just want to scale the system within the cluster. We actually need to scale the system in the cloud. In the cloud, there has already been the storage engine, not storage engine, the object store, right? We're called S3. In AWS, it's S3, right? In Google, there's some other, right? But we actually can store data in the S3, and then we can decouple the compute. We just use the EC2 as a compute node, so that if we want to scale from one machine to 3 machines, the only thing we need to do is to, add more EC2 instances, right? That's how we can scale the system at cloud scale, right? That's how the modern OLAP systems and the stream processing systems build their architecture, internal architecture. That's the other similarity. So yeah, that's just one technology, but there are another technology is called tier storage, right? As I just mentioned, well, definitely we can have the decoupled compute and storage engine, decoupled compute and storage architecture. But the problem here is that if we always put my states in always put my storage in the S3, Then the problem here that for S3 success is pretty expensive, right? Not just because for the access, the put and get cost money, right? Actually, AWS charges money for put and get. But also because, well, I mean, it actually have to, the S3 access is super expensive, super slow. It actually can take up to 100 or 200 milliseconds to complete a put and get action, right? So it's kind of expensive. So that's why we actually want to minimize the access to the S3. How do we do that? That's why modern OLAP and the stream processing systems adopt the technology called the tier storage. The tier storage, the idea is that we can always persist the data in S3, but we can actually cache my data in EC2 local storage, right? Because for anyways, for EC2 has its own storage, we can always cache it within the local storage. So using a tier storage, we can best utilize the cloud storage because we can we can try to minimize my access to S3. Right? As long as it hits my cache, I do not need to access S3, and I do not need to pay the money for AWS, right? So yeah, that's how that's also another similarity in terms of the underlying architecture. Then, okay, we talked a lot about the similarities. We talked about the similarities in terms of the architectures. Also talked about the similarities because right. And but now we want to talk about the differences. How modern OLAP and the stream processing systems are different from each other, right? I mean, so look, well, OLAP databases are mostly optimized for, interactive analytics, while stream processing systems are mostly optimized for monitoring and alerting applications. Think about, okay, if I want to answer a query like answer ad hoc queries or have interactive analytics scenarios like calculate the sales volume of a bottle of water over the last past day, or calculate the number of users in each city in the past 6 hours, probably or even 1 hour, right? For such kind of ad hoc queries or interactive queries, it's better to have real-time OLAP database systems. But if you want to do something like, monitor the account that makes over 100 transactions within the last 10 minutes, or monitor the money spent by user in each city within the last probably 20 seconds, then you actually need to, for such kind of fixed patterns or for such kind of predefined queries, it's better to have a stream processing system. Why? Well, under the hood, the technology-wise, the huge difference is that for OLAP, it actually implements the full computation mechanism, while for the stream processing, it actually implements the incremental computation. For incremental computation, it's definitely optimized for. Every time a new tuple comes in, I can update my previous query answer, right? But for the full computation, every time we trigger a query, we actually need to do the computation from scratch. That's why we have such kind of difference. That is for, real-time OLAP is better for interactive analytics, while stream processing is better for monitoring and alerting. So I'm not the only person that have summarized this. Actually, Google has a paper called NAPA. I'm not sure how many people read this paper, but if you read, there's NAPA is essentially the most of, Google's most powerful data warehouse. Well, in-house warehouse. I don't know whether we can have access to it. Well, I don't really think that they sell it in Google Cloud, but it's their most powerful data warehousing. And in this paper, if you check the it's figure 1, they actually proposed a theory called impossible triangle. That is, across these 3 properties, the freshness, cost, and query latency, you cannot achieve all of them. You can only achieve 2 of them. At most, two of them. So what is freshness? The freshness means the result freshness, right? The result, how is my result fresh enough? Is the result is, well, generated within the last 1 second, or probably generated within the last 10 seconds. For query latency, it means that the ad hoc queries latency, meaning that okay, if I issue an ad hoc query, how fast we can get a return, right? So they have such kind of triangles. And for freshness, if you really want to optimize for freshness, what do we need to do? We actually need to build the event-driven architecture, right? We actually need to do the event-driven computation. And we actually need to predefine the queries so that the system can do incremental computation. But if you really want to optimize for query latencies, I really want to run a query and return my results within a second. Then you'd better to have a user-driven model and do computations so that to do full-scan computations so that you can optimize for the ad hoc queries. So what systems are optimized for freshness? Stream processing systems are optimized for freshness. For RatingWave, well, I mean, it's highly optimized for freshness. Well, I mean, think about, well, I mean, RatingWave use cases, I mean, the two major use cases, or probably the top three use cases, let's say the fintech trading, right? Well, that's financial services. And the second use cases will be the gaming, right? Well, and the third one will be the, let's say, the IoT and also some delivery apps, right? And these are the, I mean, for this kind of think about trading, they care a lot about the freshness. Right? They probably do not really care too much about the ad hoc queries, right? Well, the quants or traders will not just issue ad hoc queries during the trading time, right? But they really want to see the fresh results. And yeah, stream processing systems are optimized for freshness. But what about is there any system optimized for query latency? Yeah, that's the OLAP database systems. OLAP database systems are heavily optimized for the query latency, because well, I mean, let's say that if you want to build a dashboard, especially those dashboards that can drag and drop, right? For this kind of dashboard, I don't really want to have I don't really want my users to have a super bad experience. That is why I drag and drop, and then the result doesn't really refresh, right? We don't really want to have such let our users to have such kind of experience. So we need to have to use the OLAP database systems that were like Pinot, right? Like others. But yeah, and so again, well, I mean, for the OLAP database systems, they are optimized for the query latency. So is there any system that is optimized for cost? Well, actually, there are some systems optimized for cost. Well, that is, well, actually, essentially the real-time OLAP, the data warehouse systems. Well, I mean, look, well, Snowflake is super expensive just because of their, it's super expensive, and just because of their pricing model. But essentially, if you ask me about the technology, I mean, these guys, well, I mean, Snowflake, Redshift, BigQuery, these guys will actually store data in S3 and store a huge amount of historical data in S3, right? So essentially, technical-wise, well, it should be cheap enough because well, S3 is always cheap compared to a local machine, right? And so these guys should be optimized for, I mean, the cost, but yeah, for some reasons they want to charge you more money, right? But yeah, anyways, well, that's with the impossible triangles. And if you're super interested in this, well, I mean, these triangles, then probably you can check the Google's paper, their NAPA paper. Okay, and then that's a trade-off. Now let's talk about the technology. Is there any difference between the technologies, right? Well, in the technologies, right? So let's talk about the storage and computation. Right? For storage, I mean, stream processing systems by default use a row store, and row store is like this, right? Yeah. It's kind of it's kind of straightforward, and it's optimized for row store. What is it optimized for? Row store actually optimized for append-only ingestions, right? If you want to ingest the data, you'd better to use row store instead of column stores or other formats, right? And the row store is also definitely optimized for point access, right? If you just want to randomly check a data point, like say, okay, look, well, what's the pricing? Today's pricing, this moment's pricing of Tesla stock, right? You don't really want to do a full table scan. You just want to do a point access, right? That's the row store. And So stream processing systems, well, most of the stream processing I've ever seen as well actually use the row store. They are actually optimized for append-only ingestions and as well as point access. But for OLAP databases, well, I mean, they are optimized for different things. Well, I mean, they are optimized for long-range scans. And if we want to use optimize for long-range scans, well, definitely by default, we need to use the column store, right? That's how that's the storage. That's how these two different systems are different in terms of the storage engine. And now let's talk about the computation. For the OLAP databases, they are heavily optimized for ad hoc queries, right? How they can optimize for ad hoc queries? Well, they actually use these two technologies. One is the vectorized query engine, right? Vectorized execution engine. And the second one is the column storage. Vectorized execution engine means like, I mean, they can use both instructions, CPU instructions like SIMD instructions, right? And to do the queries in parallel. And for column storage, because the data within the same column are storing continuously, so it's also better for the scan. So OLAP database systems use these two kind of technologies to optimize for ad hoc queries. Okay, so people will ask, okay, can stream processing systems be optimized for ad hoc queries, ad hoc analytical queries? Well, some stream processing databases will do adopt the vectorized engines. For example, ResinWave actually adopted vectorized engines. But well, they also need to adopt the row store to better serve the ad hoc query data, right? So if you want to have the optimal performance, you cannot just, implement one single, definitely implement one of these technologies can work. But to achieve the best of world, they actually probably need to implement both the vectorized engine as well as the column storage. That's for the ad hoc query. But what about for predefined queries, right? I just want to have some fixed pattern, like I just want to do some monitoring, right? Can I do something like, so how can we optimize for predefined queries? For stream processing systems, typically they are actually optimized for predefined queries. How do we do that? Well, I mean, they actually use the, as I just mentioned, they actually use the incremental computation mechanism. And in the streaming database, you can actually use build real-time materialized views to express your computation logic, right? That's a stream processing engine. But what about the OLAP database systems? Can they be optimized for predefined queries? Well, there are several challenging problems. For example, if you want to build, let's say, materialized views, right? Like real-time materialized views, then you actually need to think about, well, not just append-only queries, but also joins and deletes and handle updates. Because right, for every single database, you actually have to allow people to delete your data, or probably delete their own data, right? Because they have the right to forget, right? You have to allow them to delete their own data and allow them to update their data. How to maintain the materialized views? Well, how to do the stream processing while allowing people to issue deletes and updates, right? Also, for stream processing, there are some other stream processing specific semantics like watermark, like time window functions. These are specifically designed for stream. These are specifically included in stream processing technologies. Also, for the stream processing, we also need to think about how we can deal with dynamic scaling and failure recovery, right? Because, as I just mentioned, stream processing continues to run for every single day, and you don't really want to have any downtime, right? So there are definitely a lot of challenges for the real-time OLAP databases to incorporate with the stream processing technology inside the OLAP databases. So actually, there are more than just some technical challenges, right? Because people will argue that, okay, look, well, give me enough time, then I can build a better system and that can have all these kind of technologies. But again, well, no system is optimized for everything, right? Even for Google, they say that they can only pick, two of the two properties out of the three properties, right? So there are definitely more than just some more challenging issues. For example, well, I mean, how do we isolate the results? How do we isolate the results, right? Let's imagine that we have a system that can perfectly handle predefined queries and perfectly handle the health queries. Then the problem here is that, okay, luck for this single system, the resource is limited, right? I just have so many, computer nodes, and I just have, I just have so many computer nodes. Then how I can isolate resource, right? For modern systems, well, typically they actually, if you want to run the predefined queries at the same time with the ad hoc queries, typically you have to raise for the resource, right? If you have to compete for the resource, then yeah, you can imagine what will happen. So performance interference. So you cannot achieve the, so you will suffer from, okay, probably performance drops, suddenly suffer from some performance drops, or, right, well, that's not a very happy experience for the users. But people will say that, okay, look, well, I can probably isolate them. I allocate for 5 machines for the predefined queries and another 5 machines for ad hoc queries. Can we do that? Sure, we can do that, but the problem here is that you need to deal with the consistency issues, right? Because how we can sync data, because some of the data is stored within these 5 machines, while some data is stored within another 5 machines. What if I update some of the users, update one of my record, right? What will happen? We need to deal with the consistency. Everyone knows that consistency is super challenging to deal with, right? So we don't really want to spend a huge amount of efforts in addressing these issues. We need to better focus on our main focus, the user pain points, right? Yeah, definitely another challenge here that for the failure recovery model. For the real-time OLAP, because it mostly optimized for for ad hoc queries, so it somewhat can allow failures. That is, if there's failures, well, I can directly rebuild I can just rebuild in data warehouse terminology, it's called a virtual warehouse, right, in Snowflake's context. Or I can just reboot some EC2 instances and catch up with, and then do the computation again. But for stream processing, because it's continuous computation, it actually needs to maintain the internal computation states, right, to increment. So that's why it's even challenging, because we actually need to think about how we can recover the internal states. Yeah, that's some other challenges more than just the implementation one challenges. Within the last few slides, I talk about some use cases. Well, it's actually not use cases, but how people use these systems together. So we actually see a lot of people actually use the system, stream processing technology together with OLAP database system. How do we do that? Okay, the first pattern I pretty frequently see is that they actually use a stream processing system to do the streaming ETL, basically to do streaming cleaning, to clean your data, right, or to enrich your data. It doesn't really make sense if it's business critical applications. Typically, we actually need to filter out all these credential, right, or all the secret informations, right, from the right. And also, we probably really want to enrich the data. For example, in the ad recommendation domain, we actually need to join the click stream as well as the user behaviors, some user behavior streams, right? So definitely we need to do the streaming ETL and then insert data and then push the data into real-time OLAP databases so that we can serve the queries in real-time OLAP databases. Another pattern, the second pattern we are very seeing is that we can just use the real-time stream processing system to deal with the predefined queries while using the real-time OLAP to deal with the ad hoc queries. That's another pattern we are very seeing. And the third pattern, probably a little bit traditional, and it's called the Lambda architecture, right? So basically, we can use so we ingest the data into both the predefined queries, into both the stream processing systems and, real-time system. Ingest the same data into both the stream processing systems and the real-time OLAP database systems. So that we can use both the systems. Yeah, these are the 3 typical use cases, or the internal architecture we have already seen over the last few years. All right, to summarize my talk, both stream processing systems and real-time OLAP can support real-time analytics. And theoretically, it's impossible to achieve the best of both worlds at low cost if you care about cost. If you don't really care about the cost, I have nothing to say. Right? And real-time OLAP and stream processing systems are better together. All right, thanks. That's all my talk. Yeah.
Thanks for the talk. One pain point that we see with stream processing is trying to do long-term longitudinal analysis where your streaming or your fact table doesn't fully fit in Kafka. So like you have 7 days of data, but you want to do analysis over 2 years. Sure, yeah. Can you talk a little bit about how you bootstrap a process?
Okay, so I think it's definitely it's kind of related to how we implement the system. I mean, so basically for stream processing, one of the challenges here that we probably really want to join a fact table, right? Well, a data stream from with a table probably stored in S3, and the table could be pretty big. Or another scenario is that we want to join 2 different streams, but the streaming is like I want to join 7 days window, right, or time window. So for both cases, well, I mean, we have to deal with the window size could be super big, or the table could be super big. So for conventional systems, well, that's actually essentially a pinpoint of, to be honest, well, that's a pinpoint of Flink, because well, Flink actually need to have to maintain the states in RuxDB, and RuxDB is not that scalable because right, RuxDB is a single node, right? And another challenge here that Flink actually do not really support directly loading data from some of the data lakes, for example, Delta. So that's another pain point. So we actually, in RisingWave, we actually addressed the problem by actually, RisingWave is a database. I mean, we actually, for stream processing, we actually allow people to express using materialized views. But you actually can load your data from your, let's say, S3 into a RisingWave table. And, but what if the table is too big? It's not a problem in our system because we actually implemented the decoupled compute and storage architecture so that essentially most of the data is persisted in S3 so that you do not need to worry too much about the data size. Yeah, that's how we address the problem. And for time windows, yeah, similarly, we actually maintain the materialized views or the stream processing states in the S3. I mean, so that you do not need to care too much about the window size. Yeah.
So on this slide, you mentioned that for Spark and Flink, the MapReduce style, the compute and storage are basically like coupled. What do you mean by that here?
Okay, so here because well, I mean, look, in this figure, probably I should change the Spark to probably to Snowflake. But in this figure, what I mean is that well, I mean both Spark and Flink are computation engines, right? Why there are storage? You will ask, okay, why there are storage? In Flink, there are actually storage. What is a storage? That is internal state. Internal state is essentially a storage, right? It uses RuxDB, and RuxDB is essentially a keyword store, right? And it's actually a storage. But for Spark, well, I mean, similarly, Spark actually have what is called intermediate computation result, and that's actually we consider it like a storage, but you can also call it as a state. Yeah.
Got it. Thank you.
Yeah, it's similar in vein to the earlier question of having a large window size. My question is more about like long-running states, because you mentioned that the streaming engine, there's some state, but typically more ephemeral. But I'm just wondering, what's the typical strategy for dealing with state that you have to keep in?
I cannot hear clearly.
Oh,
yeah.
okay. I'm sorry. Oh, my question is more specifically about long-running states in the streaming job. What are some of the strategies of that deal with the long-running states, like computing running average for some stuff, and then how? Because you mentioned checkpoint as well, so yeah, just wondering what your strategy is.
Okay, so I actually have some other talks about how we manage the state, and it's not covered by this talk. But the main strategy we have is that we maintain the states in the, so basically, okay, so reusing this for the charts, if you if you use Flink, then again, Flink maintains its state in RuxDB, and RuxDB is for maintaining local machines, right? And if we run Flink using 3 machines, then essentially we need to create a 3 RuxDB instance, right? So how they do failure recovery? They actually periodically do checkpoint, and checkpoint the internal states into their S3. Probably the checkpoint can happen probably, I don't know, totally depends on your settings, every 10 minutes, every 20 minutes, or every 1 hour. And if you want to recover, let's say assume that one single node failed. What will happen is that they actually need to go back to the previous checkpoint, reload that, and then do computation. So how long it will take to recover my state? Well, to recover my compute, well, it totally depends on the frequency of my checkpoint. But the problem here is that, if you checkpoint frequently, then it can cause a lot of pressures to your local machines, right? But if you do not really checkpoint frequently, then you actually need to spend a huge amount of time to recover state. But in our strategy, it's more like, okay, we store the state in the S3 so that if node failed, nothing will happen. You just access the state in S3. There's no replay. There's definitely some replay, but it's kind of like second-level replay. We have a very detailed mechanism called the epoch-based mechanism, and epoch is just 100 milliseconds. So in that case, we do not really need to have a checkpoint. Basically, the state is essentially the checkpoint. Yeah.
All right, thanks.
Great session.
everyone.
Thank you.
Yeah.